right, it is now the top of the hour, and we will go ahead and get started with today's event. So welcome everyone. My name is Melissa Arce, and I will be the webinar moderator for today's event. Welcome to the fourth Masterclass Series webinar of OMS eLearning Academy. Today's webinar topic is how to benchmark your refinery's fuel blending control system. We've had an overwhelming response of 75 plus registrations from 20 countries and welcome you all and hope that you all will have a very informational and interactive session today. We'll have some house rules before we get started. Please let me go ahead and discuss these house rules. The webinar will be about 40 to 45 minutes long with 10 minutes for a Q&A session. You can enter your question in the chat box during the presentation, and it will be answered at the end of the presentation. Please remember to select everyone or select my name, Melissa Arce, to ask your questions if you were to have any. The webinar will be recorded and available on the OMS eLearning Academy website. There will be 2 question polls at the end for your input. Please give us your candid feedback at the end via the redirected Google form. Today's webinar speaker is Dr. Suresh Agrawal, the founder and CEO of Offsite Management Systems, LLC, and Academy Director of OMS eLearning Academy. Offsite Management Systems, LLC was founded in 1998 in Houston, Texas. It is chartered to provide consulting and refineries automation projects executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in the downstream refining industry and related businesses via the eLearning platform. The Academy has over 200 courses that can be taken online, anytime, anywhere, and on any device. And now I'll go ahead and turn the event over to our speaker, Dr. Agrawal.
Thank you, Melissa. Greetings, everybody, and welcome to our 4th webinar in the series. We present these webinars on useful topics to downstream refining professionals every month. So look for those announcements on LinkedIn platform. So today, we will discuss how to benchmark your refinery fuel blending control system. Now, this is a topic which is not available anywhere by anybody, and our academy had spent time from our experience to develop this topic and present to the industry in general. So we'll start with overview of crude oil products and fuel blending economics. We'll review a typical fuel blender, issues and ways to handle them, explain how do we do a benchmarking. And we do that by introducing 2 indices, and we'll discuss in detail and how to calculate from them. And then we compare the benefits and features of the methodologies used in the industry. If you look at 1 barrel of crude oil, there are many products. I mean, as a matter of fact, plus 5,000 plus products made in the refinery. Out of those products, majorities are gasoline, fuel oils, kerosene, and they constitute about 75 to 85% of the products made in the refinery. And most of it is gasoline, which is sometimes 45 to 55%. Processing 1 barrel of crude, it has a processing gain in terms of volume, about 5%. Mass, as you know, remains the same. Now, let's look at gasoline. What happens in a gasoline production? So I took an example of 100,000 barrels per day, and we say 45% is gasoline production. Taking the baseline gasoline price and all the taxes, distribution costs, refining, crude oil, etc., the profit is only 42 cents per gallon of gasoline. Now, this number could change based on the economics, the prices of gasoline in the country, and etc. But the point is that if you save 1 cent per gallon of gasoline, by automation, by strategic efficiency in the blending process, you save about $6.9 million least yearly. And if we say 300,000 or 600,000 barrels per day refinery, you can multiply that number. Now, these are the benefits which is lost in the refining process by inefficient blending process, not so automated infrastructure. So there is a potential in crude blending, and that's why fuel blending is on the mind of refinery management. If you look at the typical blender automation areas, this is it has about 11 modules, starting from lab analysis, tank form, automatic tank gauging system, DCS, field equipment, additive control system, and online and offline optimizers, blender, and terminals and dispatch system. This is a this 11 module configuration of blending is generic for a full automated blending system for any refinery. And this requires no or very little manual intervention. So the purpose of this is, what do we know about this our blending system? In my 40+ career in downstream refining, I have done 15-20 blending projects and master plan studies. And every time I go to refinery, I ask two questions to refinery management. The qualitative, I ask them, how good is your blending system? And I get an answer, oh, it is one of the best in the world. Our blending system does not need any more improvement. We don't have any issues in quality giveaway, recipe optimization. Okay. Then I ask them second question, give me a quantitative assessment of your fuel blending system. Can you rank your blending system absolutely or relatively? No, we cannot. But we know it's best in the world. We cannot give you any numbers that we don't know. Who cares? Now, this is not a make-up stories of question and answer. These are real. And I have gone through again and again over 40 years different refinery. Yet, management have a concern, which may be hidden, not spoken very well. They always feel, is our blending quality giveaway minimized? Are our blending profitable? How does our blending performance compare to our corporate refineries or with other worldwide refineries? If we have to automate or revamp our blending system, what's the budget? What's ROI? And how long will it take to get our money back? Or do we have enough trained blending engineers in the refinery who can maintain the system and execute the project? So these are the questions they're always have in their minds, but they don't know how to answer this question. So what do? They have 4 options. They sometimes award a project to companies, consultants who do conduct master plan and feasibility study. It costs around $100,000 to $150,000 for a study and takes 6 to 12 months. The advantage is, yes, it has a very detailed study and it creates a master plan for revamp. The disadvantage is that it does not address the blending in detail, does not offer KPI to monitor after revamp is done. The second less expensive option is they use refinery engineers who have been experienced 5 to 10 years and do this similar type of study. Yeah, it takes $15,000 to $20,000 per study and takes 1 to 3 months. It has a low cost, but again, it does not have enough expertise in-house to look at the blending system and say, hey, this is where we stand. I can rank it, I can see it, but doesn't answer all the benchmark question. The next option they have is to participate in an external survey like Solomon Associates, who do a survey every year, every 2 years, and they look at the APC and blending. I've seen one of those surveys. What they do sort of a survey across the industry, but does not compare and benchmark the blending system per se. So again, it has some advantage, disadvantage. So looking at all this option, our academy has developed these methodologies which takes about 3 to 6 months at the cost of $20,000 to $25,000. And it generates absolute and relative assessment of blending system. It analyzes every blending area, every blending automation module. And then it gives a detailed roadmap, how much it's going to cost and how long it's going to take. And we're going to see in very much in detail this approach. So the concept of benchmarking a fuel blending system, it starts with creating a gold standard for a fuel blending system. Now, whenever you do a benchmarking, you have to compare with something. What is your ideal situation? What is the ideal configuration? And gold standard should be refinery independent with maximum level of objectivity. What I mean by that, if I do assessment and somebody else does the assessment, their own views should not have much impact on the benchmarking system. Should be plus minus 10%. That's the purpose of gold standard. It should take into account how does it get affected by manpower, automation, HSE, health, safety and environment, and tangible benefits. It should generate qualitative and it should generate quantitative assessment ranks to compare with other refineries. It also should assess how effective refinery infrastructure for the blending system and how efficiently the blendings are executed. It should have a definite map to compare with the gold standard. And accuracy should be 10 plus minus 10%. And it should give a pretty good idea of how long it will take to achieve those ROIs. So we're going to discuss all this in detail, but these are the concepts and guidelines for creating a benchmarking. Now, I'm sure all of you are familiar with benchmarking. We do sometimes in terms of KPI for certain process or certain parameter measure. This goes beyond the KPI. So what is a gold standard? Let's look at a blends component circuit. What is the ideal configuration? So I have a two component for a single, two tanks for a single component and two tanks for a single grade. Now, if I have an ideal situation, ideal configuration, and this is real, this is, I've done refineries in USA and other countries. Each component should have two tanks, and it should have operated manual valves at the inlet and motor operator valve at the outlet. It should have sufficient pump to pump the recipe based on how much flow it has to pump to the tank. And it should have a spare pump. In case one pump burns out, it should be able to switch to another pump. Pressure controller to circulate to start the pump. Then we have a motor operator valve, control valves on the inlet of the blend header, and then before the blend header, and then the inlet to the tanks. Now, this configuration is the gold standard to completely automate the blending process. Now, if I have a 8 component blends, so I should have a 16 tank component for the 16 tanks for the components. So we compare this gold standard with what refineries have in their configuration. So this is just to give you an idea for one component circuit. And likewise, we have the gold standard for all the 11 automation modules that I discussed before. So in the concept of benchmarking a blending system, we create 2 indices to answer the question. Automation Effectiveness Index, that answers the question, how automated are blending operations? The second question we ask ourselves, Operational Efficiency Index, how well are blending operations executed? Now, the whole concept of benchmarking in our webinar will center around these 2 concerns and 2 indices that we'll use to create an index which can be used within the refinery across the world or refinery. It reflects individual refinery potential. It generates budget estimates, return on investment and payback period, allows meaningful comparison between refineries, whether it's in the same corporation or other corporation. So in terms of top-down methodology for benchmarking, the first step is we create a refinery independent gold standard baseline. We categorize each system module. We give a relative weights of significance of each module, tank form versus the analyzers and so on and so forth. And then we'll drill down each component, module component and the relative weighted significance. And you will see all this in detail. Then second step is we take the gold standard and compare with the refinery configuration. How much refinery have? It has a 8 component blends. So does it have a 16 tanks for the component or 10 tanks for the components? And how they juggle around between tank to tank. Then we assign weighted ranks for all the drill down components and composite weighted ranks of module. Then the next one we do the execution efficiency and loss benefits. For that, we re-optimize historical blend recipe for 6 to 12 months that refinery had done and compare with the executed recipes and summarize the lost tangible benefit. And we'll go in detail. So step 1, we assess the automation effectiveness of the blending infrastructure. Now, infrastructure means all things that you can feel and see: tank form, analyzer, pumps, valves, blenders, and so on and so forth. So you have 11 modules, and then for each of the 11 modules, we create a gold standard blending system or sub-module. So we look at each and every module of the blending system. Then we superimpose the manpower, automation, HSE, and benefit factors. So there are 4 factors for anything that affects the automation of not only blending, but anything in refinery, any manufacturing plant. And then we generate a generic relevance matrix based on that one. And then we superimpose a specific refinery blending system configuration, and we create the refinery specific ranking matrix. And then at the end, we create 2 indices, effectiveness and efficiency. Now, if you have attended our previous webinars, we talked about M-core strategy for the blending system in general, and specifically in general for refinery. For managed infrastructure, it comes tank form, tank engine system, field equipment, anything and everything that use to manufacture and control the system. Then we come to the control manufacturing aspect of M-core, which have control system, regulatory blend control system, RBC call it, advanced control system, online optimizer, and scheduling system interfaces. Then we go to the optimized production. It has a linear, nonlinear blend models, optimizers, and customized blend model parameters. And finally, reconcile the blend models. How did we do? What are the blend errors? Our blend models parameters updated KPI, quality giveaway, regress model parameters, update various biases. So we break down our benchmarking system into 4 areas: M-core, M-C-O-R. Now, so taking the blending system and all 11 modules, we come up with a relevance percentage matrix. It means how relevant is tank form, 9%, tank gauging system, 13%. And we come up all these numbers which total up to 100. Now, you may wonder, how did we come up with these numbers? What is the criteria behind it? What is the rationality behind it? Let's see it next. So for each of the relevance factors, there are 4 variables which are affecting those metrics. These are manpower, automation, health, safety, environment, HSE, and tangible benefit. Now, in my experience of 40 plus years in downstream refining, I saw that, okay, we can allocate the relevance factor as manpower 15%, automation 35%, health HSE 20%, tangible benefit 30%. Now, the question will come to your mind. Okay, this is what you did, Dr. Agrawal. What if I have to do that? Yes, that's a little bit of subjectivity in this assessment, but no matter how you do it, the accuracy will still remain within 10 plus minus 10%. The sensitivity is very low, and we'll see it, how it is possible. So in terms of manpower, what does it mean? It means the manpower in the field has to start and stop. closed open field equipment, tank sampling for analysis, manual tanks gauging. Not every refinery has an automatic tank gauging system, meter analyzer calibration, etc. Automation, we can do those. Manpower in terms of auto start, stop, valves, field equipment, online analyzers, tank gauging system, auto analyzers, calibration. In terms of health, HSE, tank spills due to overflowing, valve leaking, fugitive emission of tanks and field equipment, pumps tripping, explosion and fire hazard. The benefits, the real-time tank inventory, increase in blend productions, minimum quality giveaways, and oil movement, etc. So all these four variables do affect how do we rank our blending system modules. So we start with automation effectiveness index for the infrastructure. The question we ask, how automated are blending operations? Based on a survey of blending system facilities, instrumentation, hardware, and software, we use a proprietary methodology to evaluate each of the module. Then we find the index, the correlating, and to require investment to increase automation. An index is accurate within plus minus 10% accuracy. So for that, we have to create a scale. Now, the scale goes from 0 to 100. So what's the minimum scale? The minimum is that all the valves, all the pumps are manual. You have to turn them manually and you push them manually. You have inadequate stock tankage, manual tank gauging system, no DCS, PLC, APC. Lab analysis not available on timely basis. Recipe based on an algebraically linear model. So this is the absolute zero index. Now, I've seen this totally manually operated blending system in the refinery. Things have changed a little bit. So the next comes 100. What is index 100? It means a very automated refinery blending system. All the pumps and all the turns of valves are automatic and they are remote. They are enough and optimum tanks, stock tank for the product tanks and stock tanks. Automatic tank gauging with all required signals, temperature, pressure, and density, etc. DCS and 3 layers, 3-tier blend control optimization system, online analyzers, and all that we call it a gold standard of blending system. That's a scale 100. So all the refineries will reach, which will be between 0 and 100. There's nothing 0 right now and nothing at 100 right now. There's always a gap, even the most automated refinery in the world. So then we give the weighting to each of the areas. Now this is a cumulative and we'll go detail in each of these. So we have seen the second column and weighted ranking as 9 and other thing. And each of this ranking has manpower, automation, HSE benefits. And then we calculate and it comes out that the plant has about 5.9 of 9% accuracy. So the total cumulative index is 53.9 of 54. This is from a real refinery study. So you may wonder, how did we get this 5.9 number for a tank farm? Let's look at the next one. So for the tank farm, we go in detail. We'll drill down every aspect of it. Educate the number of paired component tanks, product tanks, automatic tank gauging system, tank alarms, interfacing, DCS, APC, stream pulling, fugitive emission monitoring, strapping table availability. And based on that, we again go to manpower, automation, HSE, and benefits, and we give a ranking based on our experience in the industry in general or in a particular refinery in particular. And then we decide that, okay, we have a 0.53 as the ranking, and our plant is 60%. And what does 60% mean? It means that if I have 8 component blend and I suppose you have a 16 component tanks, but if I have only 10, so we take 10 divided by 16 and say our plant is only 60% of what's supposed to be. And we go on so and so forth for each of the area, and we come up with the ranking 5.92. So this is the plant ranking for all the areas. It's too much to show detail for each area, but you can see the 5.9, 7.5, and we go all the way down. And finally, the automation effectiveness index comes to 54%. It means the plant, a particular refinery, is only 50% effectiveness of the automation in terms of infrastructure. So they have about 40% room to go to perfect and reach the very close to the gold standard blending system. The second question comes, okay, we have covered the automation effectiveness. How is our efficiency for the blending operation? So question we ask, how well are blending operation executed? It evaluates blend execution data against best case and worst case. It measures profit improvement potential dollar per year. It separates benefits in terms of stock economics, giveaway minimization, inventory minimization. And then it can rank against other refinery using ratio of benefit captured or profit available, or other refineries in the same corporation. So again, we create two scales, 0 to 100. For a 0 scale for the blending efficiency is batch blending. You're changing the quality of the stocks, is changing while it's blending. Linear blend models, linear optimization, if any. No stock uses economics, linear model-based recipe. So this is absolute 0 scale. This was I could see about 30 years or 25 years ago. This was the worst case. But as refinery progress, they automate. So this becomes a gold standard 100 scale of the 100 on the scale, which is inline blending, online and real-time stock qualities, nonlinear blend models, nonlinear optimization, best stock usage, inventory economics, multi-period and multi-blend planning, automatic models tuning, and reconciliation of bias and production. So now we have created two scales, 0 to 100, for the efficiency of blending. So what do we do in a step 2? If we take about 12 to 18 months of blend data, depends upon how extensive we want to conduct, and we transfer this data to a specific optimizer that we use. I'll give you a little bit idea of that one. And we get general blends, batch data, stocks, quality, product specification, and everything that is related to the blending. Now, typically, about 300 blends are executed in refinery of reasonable size of 300,000 barrels per day. So we have about 400 blend data to analyze. It could be less than that too also, but sometimes it goes to 3 to 6 months. And then we take 3-part data analysis for operational efficiency. We transform the data. The step 1, we create the minimum tangible benefits and maximum tangible benefits, the worst case scenario and the best case scenario. Then we create an index scale from actual achieved benefits and actually normalized plant index. This too much detail goes inside. There will be some webinar in the future to go more in detail. And then finally, we take the nonlinear case using nonlinear models, nonlinear optimizer, and then we estimate the stock optimization benefits, quality giveaway benefits, inventory minimization benefits. And that completes the analysis of efficiency of the blending operation. We use a sophisticated Excel-based optimizer that our company had developed. We uses a nonlinear blend models and nonlinear optimizer. And it updates the bias and all the things. And this is a automated analysis tool for those 300 blends. It's not a manual operation. Once we start the system, it takes data for 300 blends and it creates analysis. So the optimizer, it interfaces with retrieving a blend data directly from the plant or from the input Excel sheet. And then it does the nonlinear optimization using nonlinear blend models, and it generates the calculated benefits. Now, this is a study that I did for a refinery, 275,000 barrels per day refinery. And we took 3 months of data And then you can see the benefits lost was $42 million per year, which amounts to about 6 cents per gallon. Now, typically, the industry average about 2 to 3 cents per gallon worldwide. This particular refinery had very inefficient blending operations, as we discussed before. That's why the benefits were huge, really huge, about $42 to $44 million. And this is not out of the line. Typically, if you look at the industry average, the blending benefits are anywhere between $25 to $35 million per year. So we then analyze the efficiency from different aspects of the blending system, and we give the rating, and we come up with 65% as a rank for the particular refinery that we did a case study. And this number could be better for a fully automated refinery and could be worse. So how do we use these two indices? Now, we have shown that 0 index and 100 index, and we have shown that automation effectiveness index is 54% and operational efficiency is 65%. So 54 for the automation effectiveness index gives you a room that how much investment the refinery has to make to move further to 100% or close to 100% of effectiveness. And next one, 65% will show that how efficient your blending operation should be, or how efficient and tangible benefits will be realized once you move from 65% to 100%. And this is based on investment and also the tangible benefits. And this shows that typically it takes about $6 to $10 million for a refinery blending system revamp and upgrading. Taking that as a benchmark, and you get a benefit of about $10 to $50 million additional. So it gives you room in terms of ROI and in terms of the time factors. So what do we do with this thing? Now, if we take these two indices and compare them with other refineries, either in the same corporation, different corporation. Now, if you look at the number 1 in yellow, now it has moved up. It is a better automation effectiveness, but poor in operational efficiency. Compared to number 2, it has a better in operation efficiency, but not so good in automation effectiveness. And if you look at the number 3, it is on the lower side of the efficiency. So these two indices system and their comparison can give you an exact idea where you are in terms of your ranking in the industry, in the world. And also, if you have to improve upon, where should you spend money? And when you do the spend money, how much benefit you'll get out of it. So this is not an abstract benchmarking. It's an absolute and relative benchmarking system that we have developed for the refineries. Now, how does it benefits the automation project? So now depends upon refinery capacity between 50,000 barrels per day to 300,000 barrels or more. And benefits are different. If you have a lower end refinery, the inventory minimization is a more potential compared to the larger refinery, where allocation of stocks is more beneficial from the automation. So this gives you idea which area you should concentrate in terms of increased automation in the blending system. So the benefits of benchmarking system of a fuel blending is a very detailed independent assessment of blending operation at your refinery. It benchmarks against the rest of the industry in terms of two indices: how automated are blending operations, how well are blending operation executed. And then it identifies specific improvement projects with benefit for each project. It gives a sound basis for the capital appropriation. And it measures improvement over time. After you finish the project, this system will give you a vehicle where which you can do the post auditing. and seeing whether you got the money worth in real time or not. So in this webinar, we have discussed common blending issues and outlined ways to handle them. We introduced two blending indices, automation effectiveness and operational efficiency, to measure the blending facility. We detailed the generation of these two indices and their actual usage in ranking blending facility, absolutely and relatively. Discuss the usage of indices in either estimation of capital investment or post-audit purposes. That ends our presentation for this webinar. Melisha, before we have a next webinar, two webinars coming up on the crude blending. The part one will be concepts and economics, and part two will be analyzers and controls. Webinar number 5 will be held in February 6th, and number 6 will be held sometime in the future. This ends our presentation.